welcome back. Next we consider another scenario, we call it parallel plate case. When we buy substrate from market or printed circuit boards, another name is also laminate. It basically a dielectric slab and it comes with top and bottom copper plane or copper cladding. So, this type of substrate with top and bottom metallization, it can also support surface wave mode, and in this particular case we have all the TEM, TE and TM mode propagation. So, among these three, TEM mode it does not have any cutoff frequency, but for TE and TM they have a cutoff frequency. So, let us see then. This figure shows two parallel plates. These plates are in ZX plane. Again we are considering wave propagation in Z direction, and the plate separation is D. Inside we have a dielectric material which is given as mu and epsilon. For most of the dielectric material, mu r is equal to 1. So, we can simply replace mu by mu naught. So, let us first consider TEM scenario. By definition, in the direction of wave propagation, we do not have any electric or magnetic field component. So, the solution we can to solve for the electric and magnetic field, we can start with the Laplace's equation for electrostatic potential phi between two plates. So, we are not going for any solution. Let me show you directly the field plots. So, we have three scenario. This figure shows the electric and magnetic field plots for TM1 mode and TE1 mode. For transverse magnetic mode, if you look at the electric fields, they are having maximum value on these two metal planes, and the wave propagation, you remember, it is in Z direction. And for transverse electric field components, electric field are parallel to the metal plates. So, obviously, on the metal plates the electric field's value is 0, and it is having maximum value on the central plane. Now, if I compare these two scenario, can you predict in which case alpha c attenuation due to conductor will be higher? So, in the first one, transverse magnetic case, since the electric fields have maximum on the conductor plane, it will induce maximum surface current. So, it is associated with higher loss, because in the second case electric field maximum value, it is on the central plane. Now, let us look at the plot for TEM. So, this is along y, this is the normalized attenuation constant. You can think as if it is simply alpha c, and along x it is k by kc, or it increases with frequency. So, for TE1 you can see the alpha normalized alpha c is much smaller compared to other two modes as we expected. At cutoff, normalized alpha c is going to infinity. For TEM, throughout the frequency it is constant and it does not have any cutoff frequency. For both TM and TE, the cutoff frequency is same, and due to the perpendicular electric field component, for TM1 we have higher conductor loss. Now, let us start the popular wave guiding structures which we use at millimeter wave frequencies. So, this picture shows four of them. The first one is rectangular waveguide. This is nothing but hollow metallic pipe, and the cross section it's rectangle. So, it comes with different sizes for different frequency bands, and as we know, the frequency band, it is determined by the cutoff frequency Fc of the waveguide, which is a function of physical dimension. So, what are the advantages and disadvantages of this rectangular waveguide? It provides lowest loss among all these 4 different types of guiding structure. It has the highest power handling capacity, but the problem is it's bulky, it's very heavy, also it's expensive, and fabrication procedure it is also complex. We need bulk machining for this. The second example, coaxial cable, as you can see, it has one central conductor made of metal and one outer conductor. Usually we use braided shield, and this is the outer jacket. So, the electromagnetic wave it propagates through the dielectric layer, which is shown by white color here, and which sits in between the inner and outer conductor. At millimeter wave frequencies, coaxial cable is very lossy. We try to avoid them, but the main advantage of coaxial cable is that it's flexible. So, that's why most of the instrument they comes with coaxial cable for connections. This is the third example, microstrip line. This is the top view of a fabricated microstrip line. You can see the strip, copper strip, it is connected to 2 connectors or adapters, and below this dielectric slab, which is shown by black color, we have the metal ground. So, here I don't have any photograph for the ground backed CPW here. It shows the cross sectional view of a CPW, ground backed CPW. So, what is the difference between a conventional CPW and ground backed CPW is that we have one more additional ground plane here below the top CPW line, and not only that, the top leftmost and rightmost ground they are connected to this bottom ground by periodic vias. You can see it's shown by orange lines. The main advantages for this printed circuit board technologies is its low profile structure, fabrication is very easy, very simple, and cost effective. And the problems, it's lossy compared to rectangular waveguide. They have much lower power handling capability, and this is a semi open structure. So, you can see on top we have fringing field for the CPW line. So, we can't use anything very near to CPW line on otherwise we will be having coupling between this CPW or microstrip line and with that nearby structure. So, we do not have this type of problem with coaxial cable or rectangular waveguide, since it is a closed structure and everything we have inside the structure. So, these are some more structure, microstrip line, then we have packaged microstrip line. So, since microstrip line or CPW line it is semi open structure, so for practical use always we have to use some sort of packaging. This figure shows the cross sectional view of such a package. So, microstrip line it is placed inside a rectangular pipe like structure, and you can see left and right side we have that arrangement to suppress TM0 mode. You can identify the strip and the grounded via, which will suppress that perpendicular electric field component. Similarly, right side we have ground backed CPW. This is shown without any packaging scheme. We will learn later. We have also PCB form of rectangular waveguide. This is we call synthesized waveguide or substrate integrated waveguide. Also, we have PCB form of some other popular waveguides at millimeter wave frequencies like NRD, non-radiative dielectric guide, and insular image guide. So, we can we have already PCB form of the different 3-dimensional guiding structures. So, the advantages why we want to design it in PCB form, because in PCB form always it becomes a low profile structure as well as the fabrication procedure is much simple and it is much cheaper, and we can use this type of structure up to 140 gigahertz with careful fabrication. So, let us start with coaxial line. For coaxial line, as we discussed, this gray color, it shows the dielectric. Inside we have a conductor of radius A, and also we have one outer conductor. The inner radius of outer conductor is given as B, and electromagnetic wave propagates through this dielectric. If you look at the field diagram, this coaxial cable, it can support TEM as well as TE and TM mode, but for TE and TM mode we have cutoff frequencies, and below cutoff frequency we have only the TEM mode, and this is the field diagram for TEM mode. So, electric field, it starts from the central conductor and terminates at the outer conductor, and magnetic field, it encircles the central conductor. So, in this case also we can easily calculate the potential difference between central conductor and the outer conductor. Just we have to take one line from central to outer conductor and then integrate E dot dl. We can also calculate the current. We have to consider one closed loop encircling the central conductor and then calculate H dot dl. So, we can define characteristics impedance for a coaxial cable. The characteristics impedance, the closed form formula is given here. Z naught, this is equal to 1 by twice pi root of mu by epsilon into B by A. B and A, they are radii, and epsilon is the dielectric the permittivity of the dielectric which is used inside. So, approximately this is equal to 138 by root epsilon r log base 10 B by A. For most of the dielectric, we can consider mu equal to mu naught. Now, we can use a given coaxial cable till some higher frequency. That highest frequency of operation is determined by the lowest cutoff frequency of TE and TM mode. If you look at the mode chart, the mode among all TE and TM modes which appears first is TE11. The electric field and magnetic fields for TE11 is shown here. So, we have to avoid this TE11 mode excitation for monomode operation, because TEM, this is the desired mode, we do not want any other mode to be excited inside, and since the cutoff frequency for TE1 mode is lowest. So, we will consider the cutoff frequency of TE11 as the highest frequency of operation for any given coaxial cable, and the cutoff frequency is cutoff wave number is given by Kc equal to 2 by A plus B. So, from this we can calculate what is the cutoff frequency for TE11. This is C by pi into A plus B into root of epsilon r. So, it is a function of A and B. Let us say we have a coaxial cable, the inner radius is given as 0.8 millimeter and B is 2.7 millimeter. Epsilon r of the material used in between the conductors is 2.2. Then what is the cutoff frequency of TE11? If you just put the values here, we will get Fc equal to 18.4 gigahertz. We will consider a margin of let us say 5 to 10%, and this given coaxial cable we can use let us say to maximum frequency of 18 gigahertz or 18.4 gigahertz, above which we will not use this coaxial cable. Otherwise, what we expect that there will be multiple modes, TEM as well as all these undesired modes. Some applications. Whenever we measure this structure, this is showing one vector network analyzer which we use to measure the scattering parameter of any wave guiding structure as well as of any components. It can be microwave or millimeter wave components. Now, as we discussed that the guiding structure that these instruments use is coaxial cable. But let us say we are designing something in microstrip line, then how to measure my component by using coaxial cable? So, we need adapters. Adapters here already we have seen one. You see, this is the microstrip line and this is called adapters. So, it will change coaxial mode to microstrip line mode. So, we are using these adapters for measurement purpose. Now, we can easily connect our coaxial cable to left hand side or right hand side for measurement purpose. So, one end of this adapters then always a coaxial line. Now, we see we have different types of adapters available. The first examples are called BNC connect, sometimes they are also called connectors, and this is the threaded version of BNC, we call it TNC. They are typically used below 1 gigahertz. So, we usually use this type of connectors for low frequency operation or for biasing active devices or biasing the low noise amplifier or power amplifier at millimeter wave frequencies. And then we have some popular guiding adapters. The first category is SMA or sub miniature version A. Typical operating frequency range is DC to 18 gigahertz. And how we determine this highest frequency of operation? So, you remember that it depends on A and B and also epsilon r. You can see the white material inside, this is actually Teflon, for which dielectric constant is approximately 2.1. We also have N-type connectors. So, N-type connectors was designed in 1940s, it came long time back, and typical operating frequency is DC to 18 gigahertz. Here we have pictures for male and female type N-type connectors. So, among these most popular connector at microwave frequencies is SMA or sub miniature version A. It came in 1960s. So, right side this picture shows different types of this first line, different types of SMA adapters. So, we have male and female type, and when you are ordering for different connectors, you have to be very careful about the male, about the mate. Now, at millimeter wave frequencies, we have similar connectors. The first one, it is called K connectors. If you look carefully inside, it looks like one SMA connector, but its inner dimension is different. Not only that, you can't see any dielectric inside, it is actually air, and the central conductor, it's as if it's hanging in air. It is supported by very thin layer of dielectric actually, and this is called K connectors since they are popular for K band operation, all these 3 K bands. Next we have V connectors for V band operation. The highest frequency of operation is 65 gigahertz. So, left side is female, right side is male. We also have 1 millimeter connectors. Its outer diameter is just 1 millimeter for 110 gigahertz operation. So, this is the chart for different type of connectors. We have N type, we have 7 millimeter or APC7. APC7 it is a sexless connector. SMA, we have super SMA, it is used till 27 gigahertz. 3.5 millimeter, 26.5. So, you remember the highest frequencies, it is determined by the cutoff frequency of TE11 mode. So, when you order your coaxial cable, you be careful about the highest frequency of operation. Next waveguiding structure is the rectangular waveguide. At millimeter and terahertz frequency, most probably it is the most used structure. A typical rectangular waveguide, it can be air filled or it can be dielectric filled. So, here let us start with one dielectric filled waveguide. So, inside we have a dielectric material which is defined by its mu and epsilon. Now, a rectangular waveguide, already we know it can support TE mode as well as TM mode. If you and which one is the fundamental mode? It is TE10 mode, right. So, TM mode, it appears later, and for normal operation we always use this TE10 mode. So, let us go through the basic relationships, then we will consider what are the problems or characteristics we have at millimeter wave frequencies. So, the energy transport velocity or group velocity, it can be given as c into square root of 1 minus omega c square by omega square. So, group velocity becomes a function of omega, right. It varies with omega. So, it is always dispersive. Once we have group velocity, we can easily calculate phase velocity. They are related by this expression. And now, in general, the cutoff frequencies of TE and TM modes can be given by this expression. So, M and N, they represents the mode number sorry, and A and B, they are the rectangular waveguide dimension. So, A sorry, A is the broadside dimension and B is the thickness of this rectangular waveguide, and then it is associated with a cutoff wave number. Beta, it can be given by square root of k square minus kc square. We can put the values of kc here. This is the cutoff wave number. If you look at the attenuation constant, the closed form expression alpha c, this is equal to 8.686 into Rs by eta b. Rs, this is the surface resistance, eta intrinsic impedance, b is the thickness of rectangular waveguide, and it is again a function of omega. Look at this expression. At omega equal to omega c, this factor cancel out. So, at cutoff alpha c, it becomes infinite. As we increase frequency, alpha c, it decreases. Alpha d, it is equal to k square tan delta by twice beta, but at cutoff again beta is 0. So, alpha d, it is also infinite at cutoff frequency, and it is a function of frequency as well. So, we see what alpha c and alpha d both are function of frequency. Now, let us consider the fundamental mode TE10 mode. So, for this one we have if the wave propagation in z direction, then by definition Ez equal to 0, and if we solve for the other field components, we can show that here we do not have any Ex component, we have only the Ey field components, and the variation of Ey, it can be given by this sinusoidal relationship. So, at x equal to 0 and at x equal to a, electric field, that is 0, and it is maximum on the central plane. So, it shows the vector electric field distribution inside a rectangular waveguide. So, if you follow this line along the direction of propagation, they are not only maximum on the central plane, and you see they are varying periodically along the direction of propagation. So, it is maximum here, then it decreases minimum, then it changes its direction and again it decreases. So, it also varies periodically in the direction of propagation. We can also plot the scalar electric field distribution inside the rectangular waveguide. This is the plot. So, this is basically field strength versus x and y. We have maximum shown by these red lines and the minimum values are shown by blue lines. So, let us take a short break, then we will discuss about alpha c and beta variation with frequency and how it behaves at millimeter wave frequencies.